Well, welcome everyone to GeoHug. So I'm so excited. We've got Laura Morrissey with us today. But before we do kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation. And I'd like to pay my respects to the elders past, present, and future. And yes, I am super excited that we have Laura Morrissey with us today. So Laura is currently a research fellow at the University of South Australia. She's a metamorphic petrologist who applies her knowledge of mineral behaviour to understand a variety of larger questions relating to tectonics, high temperature processes, and ore deposit genesis. So it is going to be brilliant hearing from her today about her research on revising the mineral province correlations of North and South Australia. So it's going to be a fantastic session. I hope you all enjoy it. I'm promoting you all up as panelists. Please don't be shy. Come through. You can get the cameras on and the mics on. And at the end of the presentation, we'll be opening up the floor. But yes, thank you so much, Laura, for joining. It's awesome having you on here today.
Thanks, Jess. Thanks for inviting me.
It's so good. I was really curious what got you into geology to begin with.
I was a bit of an accidental geologist. I think lots of people are accidental geologists. So I'm not very good with blood, so that ruled out biology. And then I just happened to do it at uni to fill an elective, and I really enjoyed it. So I was doing law at the same time, which was a completely different, you know, it was very sort of lecture-based without any pracs and felt a bit isolating. Geology was just so much more fun. So I ended up continuing on with it.
Oh, I love that. That's amazing. And what have been some of your favorite things, some career highlights so far?
Well, I think with geology, we're so lucky that we get to travel. So probably one of the things that kept me in geology and doing a PhD and things was the ability to travel. So I've been to all 7 continents with geology now, which is a pretty good milestone. So
that's amazing. Oh my gosh, that's really cool. Wow. And I always ask speakers to bring along a favorite pet rock, and I understand that yours is quite big. So you've got an awesome picture for us today of your favorite pet rock. Can you give us a sneak peek?
Yeah, I'll just share my screen. Yeah, so this is a Ediacaran fossil. So as you know, in many of you would know, in South Australia, we're really lucky because we have the Flinders Ranges just on our doorstep with really awesome Ediacaran geology. So I was in the field with my paleo friend, and she was doing proper geology, and I was just wandering around, and I happened to find this fossil, which is a Dickinsonia rex, which is pretty rare. At the time, I thought it was the first time anyone had seen 2 of these interacting with one another. So I thought that's nature paper. There we go. Didn't turn out to be the case. It's actually one fossil, but what is cool about it is it's one that's been injured, and then it looks like it's actually trying to heal and regrow. So I think it's probably the coolest fossil my friend had ever come across, and I just found it randomly on the side of a hill. So this is my pet rock.
That is a phenomenal pet rock. Thank you so much for showing us that. That was so cool. And yeah, thank you so much again for being here. Yeah, if you want to get stuck in, and yeah, I'll open up the floor at the end. Thanks so much, everyone.
Change tack now from sedimentary geology to rocks that have had a bit more happening to them potentially. So this, as you'll see as I go through, is very much a group effort. It's work that has been done by some of my PhD students over the last few years. And they've actually just finished. So it was really nice to get an invitation to present this and to put all of this work together and take all of the different things and different studies they've done and put it into kind of a broader tectonic framework. So why put it into a tectonic framework, I guess, to start with? Well, we know that globally there are particular deposit types which are more common at particular times in Earth's history. And that's thought to be related to the supercontinent cycle, with the idea that at different points in the Earth's history, the tectonic regimes which were kind of operating were much different. And so we had the different sets of ingredients which drive different styles of mineralization. So if we can put a piece of crust into that framework, It can give us a broad scale idea of what we're looking for, the styles of mineralization that we're looking for, and even the spatial scales of mineral systems that we might be looking for. It can also help us to draw regional correlations. So in the Gawler Craton, or in Proterozoic Australia in particular, we have a lot of crust we don't understand very well. So if we can try and correlate that to areas where we do have outcrop and we do have information, it might give us a much better sense of what we're looking for undercover. And then I guess the potential for preserving these deposits when they're formed. If we know what's happened to a piece of crust at a point in Earth's history, we then get a sense of whether it's likely to have preserved any deposits it may have formed. So that's why we try and put these things into a mineral systems and a big supercontinent framework. And in the context of Eastern Australia, which is what we've been focusing on, what we're thinking about is where it fits into the Lunar supercontinent. So in the late Paleoproterozoic to early Mesoproterozoic, Australia really sits in the Lunar supercontinent, and it's an important part of that Lunar supercontinent. It's thought to be one of the final pieces to amalgamate to that supercontinent in the late Paleoproterozoic. So it means if we're thinking about Eastern Australia, we need to be thinking about what's happening on that margin between Australia and Laurentia in the late Paleoproterozoic, and then potentially a little bit less so what's happening on the margin between the Gawler Craton and the West Australian Craton. So the timing and position of Australia relative to Laurentia and even relative to Western Australia is still debated. When they finally came together, when they broke apart, all of these things are debated, but they are the framework that we need to put our data into. So we think about Proterozoic Australia in terms of three kind of cratonic elements. These are defined partly on geography and also on slightly different geological histories. This was put together in 2016, this map. I like the colours, but it's actually probably already a little out of date, because over the last 5 to 10 years, there's been a lot of work trying to understand those margins between these three cratonic blocks and how they fit together, how they've reoriented through time. And that work has found that potentially Western Australia came in a bit later than we previously thought, so maybe only turned up in the Mesoproterozoic. But everyone, I think, is pretty happy that there are links between North and South Australia in the Paleoproterozoic. So that's based on paleomag constraints, but also based on geological constraints as well. So one of the sort of early links and strong links that we have is the Cairn province in South Australia and the Mount Isa province in North Australia. They have a strong connection. So they have very strong correlations in their sedimentary rocks in terms of their timing and their stratigraphy. And what we see, to the point where people even use thicknesses in one region to correlate with thicknesses in the other, where we may be missing part of the record. They also have quite strong correlations in the sort of Mesoproterozoic, with the Alarian orogeny corresponding in timing to the Eisen orogeny. The Northern Gawler and the Aileron province also have been something that has been linked for quite some time. So the Northern Gawler Craton is not well exposed. There's not a lot we know about it, and everything we do know is essentially from spatially spread out drill holes. But those drill holes intersect igneous rocks and sedimentary rocks, which look very much like rocks in the Aileron province. So geochemically, isotopically, and age-wise, those igneous rocks seem to correlate with rocks in the Aileron province, and then the detrital zircons from sedimentary rocks in the Northern Gawler also match the timeline of events in the Aileron province. So that's another connection which is fairly well established now. As we go further back in time, as you can see, we have much less to work with, but sometimes this connection's actually been extrapolated back all the way to the late Archean. The Eastern Gawler Craton and the Cairn province also have been linked. So the Adelaide Hills, where I live, is underlain by a metamorphic complex called the Barossa complex, and that is linked to rocks in that have experienced metamorphism during the Alarian orogeny in the Cairn province. So in terms of thermal gradients and structures, these two areas were also linked. And then the southern Gawler Craton, eastern Gawler Craton and Cairn province have a similar magmatic history. In the eastern Gawler and southern Gawler have the Hiltaba magmatic event and the Gawler Range volcanics, which correlates to the Venadru Ridge volcanics and granites in the Cairn province as well. So when we put all that together, you can see that there is quite a strong argument for a connection between all of these regions in the Paleoproterozoic. When we get to mineral systems though, they're a little bit younger and things are a bit harder to start correlating. So it's tempting to correlate them because we have IOCG mineralisation in the Gawler Craton, we have IOCG mineralisation in Mount Isa. They are broadly Mesoproterozoic, early Mesoproterozoic, but when we start looking at their ages in more detail, you can see they don't quite match up. So the Gawler Craton mineralisation is dominantly between about 1590 to 1570, whereas in Mount Isa, it's a slightly longer duration of mineralisation and it goes to younger ages, so down to 1500-ish. So temporally, when you look at them more carefully, it doesn't look like they necessarily correlate, but maybe we have the ingredients we need for mineralisation, even if we don't have that temporal connection that we can use to correlate them. So obviously, Olympic Dam has dominated a lot of the mineralisation research in South Australia for a long time, for very good reason. It's by far the biggest deposit we have. So the key ingredients for IOCG deposits in the Gawler Craton are really thought to boil down to you need Hiltaba magmatism, so high temperature magmatism with a mantle component that gives you metals, it gives you heat, and it gives you fluids. Unmetamorphosed sediments, so the Wallaroo group is a unit in the eastern Gawler Craton, and that's thought to play a role by contributing extra fluids as well as the potential for chemical traps. And then geochronology, not all of these deposits have been dated, but the ones that have always come out somewhere between 1590 and 1570 MA. So that's all the big IOCG deposits that people have done geochronology on. And that matches with what people think, that there's a real connection with the Hiltaba magmatism in the eastern Gawler. Eastern Mount Isa has some similarities, but then in other ways looks a little bit different. So it's thought that there's quite a role for Williams-Narraku magmatism. So that's another high temperature magmatic system that has mantle input. Looks like there's a role for major structures because lots of the deposits sit proximal to these structures. There's regional highly saline fluids, and those saline fluids are oxidized, which is thought to be important for moving those metals around at a regional scale. And then temporally, there's a much bigger time frame for mineralisation. So it goes from about 1600 to 1480. But the peak of mineralisation is thought to correspond approximately in timing to Williams-Narraku magmatism. So that suggests that Williams-Narraku is a really important ingredient and driver there. So that kind of brings us to when we try and put them together and draw correlations. In both these cases, we might have the ingredients we need, but we don't necessarily have the same tectonic drivers. And so if we're trying to use these correlations to drive an exploration model, we need to think about two end members. One is that we have a tectonic driver, but in those cases that those tectonic drivers are different, and that explains the temporal differences. Another is that it's essentially the same geodynamic regime, but the locus of mineralisation and the locus of what's driving that mineralisation changes through time. So if we're thinking about an exploration model, the end members are that we have different drivers for mineralisations versus they form in a single evolving regime. Oops, sorry. So if we take Mount Isa as an example, and the Williams-Narraku magmatism as an important component or an important driver for mineralisation, people have tried to put that into a tectonic model. And the most recent model suggests that it's the result of post-collisional extension. So we have Laurentia coming in around 1600 MA, and then the Williams-Narraku magmatism is the result of extension following that event. So they've put that into a tectonic model, and that assumes that processes happening on the eastern margin of Australia are what's driving the mineralisation in Mount Isa. People have done similar things for the Gawler Craton. It uses a different margin. So this uses the southwestern margin of the Gawler Craton and the St. Peter's Sweep. But again, people have taken observations and tried to come up with a model that places the Olympic Dam mineralisation into this sort of tectonic framework. More recently, though, people have looked at Olympic Dam. Claire Wade at the Geological Survey of South Australia did her PhD on the Hilltopper magmatism, and what she's concluded is that it's a felsic-rich large igneous province, which is consistent with being driven by a mantle plume. So the geochemistry and isotopes of the Hilltopper rocks look like they're consistent with a mantle plume. Liz Jagodinsky has done high precision geochronology and found that the Gawler Range volcanics extruded over a relatively short time period. Hilltopper magmatism extended slightly younger, but all in all, the whole event was over and done with somewhere between 1595 to 1580, roughly, with mineralisation really concentrated in that early part of the interval. So if we have a large igneous province, that's effectively independent of those tectonic reconstructions and regimes, which means it's hard to actually correlate a tectonic, an overall tectonic setting and try and fit the mineralisation into that if it's actually being driven by something that's independent of the tectonic regime. So obviously we've focused a lot on the Olympic Dam because it's such a big deposit, and the large igneous province locus, so Olympic Dam and Prominent Hill and Carapatina. But if we look beyond that, are there other things we can correlate that might give us a connection between the Gawler Craton and Mount Isa? Which brings in the Northern Gawler Craton, which is going to be the focus of the rest of this talk. So the Northern Gawler Craton isn't as impacted by the Hilltopper event. So it has the potential to record some of these younger events that we see in Mount Isa, which might be driven by Nuna breakup and the tectonic boundary off the eastern margin of Australia. But we don't know very much about the Northern Gawler Craton. So the first thing that we did was to pick some places in the Northern Gawler Craton to try and understand a bit better. So the first one we went to was the Peak and Denison Inlier, or domain, which was Mitchell Bockman's PhD. At the time, Mitchell was working or collaborating with Minotaur, who were also working in Cloncurry. So they were very interested in testing connections between Peak and Denison and the Mount Isa region. So this is Mitchell. He's now at the Geological Survey of South Australia, but he's still broadly working in this space. So what he found was the basement in Peak and Denison comprises 1800 to 1740 metamorphic rocks with a 1550 granite intrusion. Anthony Reid's work previously had shown that sediments in the Aileron province, sediments in drill hole TB02 correlate to the Aileron province. And there was known to be calcic and chlorite alteration in the southern part of the Peak and Denison domain. Mitchell's new geochronology found that he had granitic magmatism at 1740 and metamorphism somewhere between 1490 and 1500, constrained by zircon rims and metamorphic titanite. And then he had a second generation of titanite, which he interpreted to be alteration in this sample at least, which was 1465. He also had an undeformed granite from the same drill hole, which was gave the same age as his youngest titanite ages as well. He also directly dated some of the altered rocks as well, using titanite. And what he did was got a range of ages from 1565 to 1465. So consistent with the youngest magmatism he got in the previous drill hole. And this was directly associated with calcite and chlorite alteration. So when he put it together, it didn't really look like the Gawler Craton. It's much younger. But what it did look like was the ages that people were getting out of Mount Isa. So the alteration he was seeing at Peak and Denison and the ages he was getting correlated with the Mount Isa region. So he used this to draw a connection between Peak and Denison and Mount Isa in the early Mesoproterozoic. At the time Mitchell was working there, there was no real known mineralisation, but it is now being actively explored. And D Metallica did drill some holes a year or so ago and intersected some sulfide. JU, who you'll meet in a second, is currently working on these and trying to constrain the timing of that sulfide mineralisation. And what he was getting in terms of ages is very consistent with what Mitchell was getting. So it very much looks like Mount Isa. Jay actually spent most of his PhD working along strike from where he is working now, along the Karari shear zone, which just comes down through here, at a deposit called Cairn Hill. So Cairn Hill's in the northern Mount Woods domain, and I'm sure Jay has probably had enough of Cairn Hill because he spent a lot of time there. But essentially, it was important to look at because it's a magnetite deposit, but it contains some copper as well. So it was thought to be part of that IOCG family, but a deeper expression of that IOCG family because it contained magnetite rather than hematite. It's also important because the Mount Woods domain looks like it's Gawler Craton proper. So it contains Archean to Paleoproterozoic basement, which looks very much like the central Gawler Craton. And it also contains Hiltber magmatism. So it's that connection with the eastern Gawler Craton. Sorry, someone just knocked on my door. So Cairn Hill sits at the northern margin of the Mount Woods domain. And as I mentioned, we looked at it as part of that IOCG family. It does look a bit different. So it's very deformed. So it's amphibolite facies, deformed rocks. They host magnetite, apatite mineralisation, which is wrapped by hornblende selvages. And then we have this late brittle pyrite, chalcopyrite coming through with a second generation of apatite. So Jay did some really careful geochronology and really texturally constrained geochronology. And what he found was that the zircon in those hornblende selvages gave an age of 1580. And that was pretty consistent with what we thought we would get. We thought it would be connected with the Hiltber. We thought it would be part of that Gawler Craton Mount Woods story. He also found that monazite within the gneissic host rock gave an age of 1580, but then another age of 1490. So he interpreted the magnetite mineralisation to be 1580-ish, and that deformation, amphibolite facies deformation, to be 1490. He also dated lutetium hafnium with lutetium hafnium. He dated coarse grain apatite within those magnetite zones, and what he got was an age of 1490, which was consistent with the age for metamorphism. Lutetium hafnium in apatite tends to give, it's much more resistant to being reset than uranium lead in apatite, and so it's able to give older ages usually. Importantly, he also then dated the second generation of apatite, which is visually and chemically different, and it sits within the pyrite and chalcopyrite, and he got a younger age of 1460 MA. So when he put that together, and he also was very careful and collected in situ monazite geochronology within that apatite, and that gave a uranium lead age of 1460, which backed up his lutetium hafnium age. So when he put it together, Cairn Hill looked a lot more complicated than we thought originally. We had two mineralisation events. So we have a magnetite mineralisation event at 1580, and then a copper mineralisation event that came through at 1460. But these were separated by 100 million years and a granulite facies metamorphic event. So they're temporally unconnected with one another. Interesting though, when you start looking at the ages that Jay was getting from Cairn Hill and even the youngest ages that Mitchell was getting for alteration in Peak and Denison and that Jay is now getting from his new samples, these post-date what we're seeing in Mount Isa. So if we go to Mount Isa, this area is being looked at again by Brad Cave, who's another PhD student who just finished from Adelaide. And I'm just going to focus on the Hilton and George Fisher deposits and the Mount Nobbit deposits. But what he did was revisit these and collect geochronology from them. So the Hilton George Fisher event, which is the most northerly deposit that I'm going to mention from Western Isa, Brad got some monazite from this, which gave an age of 1513, and some calcite lutetium hafnium, which gave an age of 1500. So he interpreted that Hilton George Fisher mineralisation occurred around 1510, which is similar to ages elsewhere in Mount Isa. More regionally, he and I have looked at some of the amphibolite facies metasedimentary rocks in the area, and what he tended to get in terms of the monazite, it's a bit messy, but it falls into two broad populations at 1650 and 1570, which corresponds to known tectonic events in Western Mount Isa at the time. But there's also green schist facies shear zones at 1440 and apatite uranium lead ages, which also are much younger than the monazite. So this suggests we have metamorphism, amphibolite facies metamorphism, that's a bit older, but the whole thing is experiencing a green schist facies overprint at 1450. And that's kind of interesting because what he then gets for mineralisation at Mount Nobbit suggests this might be quite important. So he dated some monazite within foliated biotite, which he interpreted to be pre-mineralisation, and that gave an age of 1527. Whereas monazite within the carbonate alteration gave a much younger age of 1457. So he interpreted mineralisation at Mount Nobbit to be around 1460 MA, which is approximately coeval with those green schist facies shear zones. In terms of the regional metamorphism here, he got much younger metamorphic ages, or we got much younger metamorphic ages for the amphibolite facies metasediments. So a peak at around 1510 and 1460, as well as chlorite-bearing schists at 1450 as well. So when you put it all together, we're starting to extend this timeline from, in the Gawler Craton, everything being pre-1590 essentially, and in Mount Isa, everything being about pre-1500. These new techniques and by revisiting some of these areas, we're getting much younger ages, which show that the story might be a lot more complex. And we actually have potentially the potential for mineralisation down to much younger ages. Tectonically, these younger ages have sort of been known in the Gawler Craton, but no one has really known what they mean. So argon-argon has consistently given ages of around 1450 in the Northern Gawler, but this was interpreted to be a combination of either minor shear zone reactivation or cooling. But importantly, now we're starting to get evidence for metamorphism, magmatism, and alteration at this time, suggesting it's actually probably a much bigger deal than was previously thought. When you rotate the Gawler Craton into its Mesoproterozoic orientation, it's thought to need to be rotated about 51 degrees counterclockwise, very precise according to the Paleoinvac. But when you do that, a lot of the structures we have in the Gawler Craton, which are approximately east-west now, actually end up being more or less north-south-ish and in a similar orientation to what we see in Mount Isa. So it looks like in that sort of northeastern part of the Gawler Craton and in that southern part of Western Mount Isa, we're really seeing a record that's extending younger than 1500, potentially down to 1450 in terms of metamorphism and shear zone activity and things like that. In terms of Laurentia in Australia, this is the period where we think that Australia started to rift off Laurentia. So we don't have very many diagnostic pressure temperature assemblages for rocks of this age yet to tell us what the thermal regime is, but the ones we do have suggest that they're high temperature, low pressure metamorphic rocks, which is consistent as well with regional basin formation across Australia at that time. So potentially we have a big extensional system, which is driven by Australia and Laurentia rifting apart at this time. But that's important because if we're extending the crust, we may have the potential to be refertilizing it and putting new metals into the crust. So all of that's going to feed into any sort of mineral systems model that we put forward for this time. So I guess just to conclude, as someone who's worked in the Gawler Craton for a really long time, there's more to it than the Hillsborough event. So stay tuned for the potential for a new mineral system to be sort of explored in the northeastern Gawler Craton. Even in relatively mature terrains, we're finding that we can collect fundamental information if we're starting to target different styles of rocks and different styles of minerals for geochronology. And that has the potential to define new alteration or mineralizing events, even in areas that we thought we really understood. And increasingly, we have strong correlations between the Northern Gawler and Mount Isa in the early Mesoproterozoic. And that's not just in metamorphism and high temperature events, it's in things like alteration and mineralization. I guess the final takeaway is it's really important to understand the continent scale tectonic regime, because that's going to give us a broad scale guide, but we need to correlate both the ingredients for mineralization and the temporal framework if we want to use these to inform mineral exploration models. And in the context of this young record in Eastern Australia, I think that's what we're lacking. We're starting to get that temporal framework, but we don't really have the ingredients so far to know what that's going to mean for a broader scale mineral system. So thanks for listening. And that's really all I had to say so far.
That was awesome. Thank you so much. I hope you all enjoyed it, everyone.